Hi there. This is Ryan Chatterson, and today we're going to talk extensively about aquaponics system engineering and design fundamentals. So we'll start off with why do we want an efficient aquaponics system design? Okay, well, for one, we're going to have lower startup costs. By choosing the right equipment and not oversizing the equipment, our startup costs and potentially the quicker ROI is going to come from choosing the right equipment. So we have a lower startup cost. We have lower running costs. So when you choose equipment that's too large for the application, it not only costs you money up front, but it continues to cost you money in power usage throughout the life of that product. We have better quality fish and vegetables. We are providing the correct environment for the fish and vegetables so they've got a better quality of life. And that's going to lead to less diseased and healthier, faster growing fish. And the plants are also going to be less diseased, less problems, less influxes of pest presence, and a higher nutrition quality because they're actually getting what they need. We have a more robust system. So you design it correctly, you don't use the cheapest parts available, you use the correct parts for the job, and it's going to last you a long time. This is not something that you're going to have to rebuild every year or every other year. It's going to last a very long time. There's less maintenance issues because you're using the correct items for the job. You're not going to have them breaking down all the time. And that's a really good thing when you're running a farm and you're taking care of and raising living creatures. So not just plants, but fish. And it will stand the test of time. Again, 5-10 years down the road, you're not going to have a problem with degrading parts, things like that. There will be some maintenance issues, but the bulk of the entire build is built to last. So we're going to go ahead and start off where it all began for me and where I think everybody else needs to start at and take another look at. And that's the University of Virgin Islands system. The original aquaponics system that I came across when I was starting my journey, and that still has stood the test of time. It's still running today. So we're going to do an overview of the University of Virgin Islands system. University of Virgin Islands aquaponics system is the longest running and most researched system to date. The design was published in 1992, so that can give you an idea of how long we're talking about here. It's a low-cost design. It wasn't meant to be state-of-the-art, highest-price equipment than you can find. It was meant to be an affordable model that would work in the Virgin Islands. There's proven results, so they have proven data year after year after year of what they can yield out of that system with a variety of different products and on the plant and on the fish side. Solids are removed and used on terrestrial crops. So a lot of people jump right away from the University of Virgin Islands model and say, oh, that's old. It was developed in 1992. There's so much new technology out there. This is not something I even want to look at. Well, I can tell you today, I can build a University of Virgin Islands system and it will be profitable. I don't think it will be quite as profitable as the system I've designed, and that's why I went ahead and made some changes. But you can make money. The big difference is you actually have to market a little bit more fish, and you're going to have a little bit more fish feed and fish waste coming out of that. But if you market and sell those fish and you don't do it at a loss, your vegetable crop is still going to bring you the same amount of money. So just to throw that out there, do not just glaze over the University of Virgin Islands system and think this is old technology. It might be old, but it is very applicable for several areas. And I spent years on built and ran a scaled down University of Virgin Islands model. And I can tell you, running hundreds of species through that model, I can still grow tomatoes, I can still grow squash, cucumbers, all the fruiting crops I grow now. We can still do it in this system. We just have to provide the other things that those crops need. So we'll get that out of the way. right here are two great links for you to click on that go extensively into the operation, the build, the specifics of the University of Virgin Islands system. And this first link is the old link from the 90s, and you'll see it's in black and white. But again, that's what we had to go off of back in the day before everything got popular. This second link is a newer article, and it's very extensive. I want to say it's 40 to 50 pages from the University of Virgin Islands about their system. So definitely great links. Give a read and look through them, and by the time we're done with this class, you really will understand thoroughly what's going on in those systems. So the system consists of 4 2,000-gallon culture tanks, 2 1,000-gallon cone-bottom clarifiers, so that's their first stage of mechanical filtration, and then we've got 4 185-gallon orchard netting tanks. So these are long rectangular tanks full of orchard netting where the flow runs through the orchard netting tanks and actually allows the suspended solids to land and stick to that orchard netting. So it's a secondary solids removal device. There's also some mineralization that occurs in this tank, but I would call this passive mineralization. This is inline, and this is not something that we're doing outside of the system. Then all the water flows to a 185-gallon degassing tank. So to get rid of any nasties that are coming out of the net tanks, any methane, any kind of bad gases or CO2 that has built up, it's to degas that before it enters the plant troughs. Then the water flows into the plant troughs, through the plants, and then back into the sump, which is the lowest point, and that is where the pump picks the water up and delivers it back to the fish in the culture tanks. Here you see feeding rates are 5.6 to 9.3 grams per square foot of growing area, or as you'll see published in the papers, 60 to 100 grams per square meter. Just a conversion there, square feet or square meter, whatever you decide to look at the information in. And here's a drawn out picture. 4 rearing tanks, very easy. From the rearing tanks, they go to the main solids capture. We have a 1,000-gallon tank here and a 1,000-gallon tank here. From the main solids capture, it goes out and runs down one tank and back down the other. So you get a long residence time through those 2 tanks. And then it finally goes into the degassing tank. So it's basically 2 separated filtration systems. They could have done this in one large filtration system, but it's pretty hard to get a 1,000-gallon cone bottom tank, let alone a 2,000-gallon cone bottom tank. So sometimes these decisions are up to what equipment is available or how hard it is to make that equipment. So you can see a very simple design. From here, the water flows out to the hydroponic tanks, and it goes out to 3 troughs, to this trough, and this trough, and the water flows down and then all the way back, and it flows into the lowest point of the system here. From here, a water pump picks it back up and delivers it back to the culture tanks. Very simple design. A nice simple flow through the equipment, through the beds, and then back to the fish tanks. Very simple. I love the design. And here's a great picture of the University of Virgin Islands system in full production. And you can see some beautiful lettuce here, 6 different troughs. They have plenty of room there, so they didn't squish the troughs right up on each other. They have enough room to move around, bring a little tractor in here if they need to. So you could picture this as far as square footage that it takes up. You could really shrink that footprint, but that wasn't needed when they built it. Here's a picture from inside. You can see the 4 culture tanks. The filtration is out here, and then the plant troughs are out further beyond the system. And you'll notice there they have shading over the fish tanks because we don't want algae growing in there, and it'll also help to keep the water temperatures down. So it didn't have to be a completely closed system. So there is some, birds could get in there. You could still get some other outside effects, but it's better than just having it out in the sun with no covering. So efficient use of materials for the build. They used they built the cone bottom clarifiers, they built the troughs out of block. So a really efficient use of material, and they didn't have to go out and buy the highest price item for each of these mechanisms to pull out the waste and to do the biofiltration, etc. The water piping was not properly engineered. So the water piping, if you look into the specifics, is very large and it does not fit into the flow requirements that we've listed earlier. The solution to this was that they actually put tilapia into the pipes. And the small tilapia swimming through the pipes would clean the biofouling and move any settled solids back down the pipe. Every so often, they would pull those tilapia that are slowly growing, they'd pull them out of the pipe and stock the pipe with new fish. So they used fish to clean the piping, which worked for 20 to 30 years. So you can't say it doesn't work. But from an engineering standpoint, we would rather size that flow to a minimum of 2 feet per second so that we keep solids from settling in that pipe. And it will also save you a lot of money on piping, because 6-inch pipe versus 3-inch pipe, something like that, that's going to be a big difference in money when you get through the whole length and all the fittings that you go through. The air distribution network affects in the culture tank, the fish culture tank, they affect the flow in the tank. So the air stones are placed around the entire rim of the tank and dropped vertically. So instead of a long rectangular stone, they're dropped vertically into the tank and hung. Well, first off, that messes up any kind of flow dynamics within the tank. That disrupts our tangential and radial flows that are going to naturally drive the solids to a center bottom drain. So that's no good. The second thing is that an air stone should always be placed flat, not up and down, because as you know, air will flow the path of least resistance. And if you have an air stone hanging vertically, the majority of the air is going to come out of the upper portion of the stone, leading to larger, less uniform bubble size and less transfer of oxygen into the water column. So you want those rectangular stones flat so that you have even distribution throughout the stone and even airflow. The waste removed from the system is removed from the system 3 times daily through those clarifiers. And it's stabilized in a pond. They dug a pond, lined it, and have some air stones in there. So very similar to a mineralization tank. Then after it's stabilized, they use it on terrestrial crops that are grown there at the university. So believe it or not, if you want to look at it this way, it's a decoupled aquaponic system. They are still using their mineralized water that they're removing from the system for terrestrial crops. It's not just going to the sewer and out, out to waste somewhere. So if we really want to get down to brass tacks, they're using all their waste product. But what we're looking to do in a lot of situations is use that waste product within the hydroponic component of the system. So that's what we'll talk about here in a little bit. And the last thing here, what are we losing by discarding that fish waste? So that's a big question, and we're going to answer it. Depending on the crops that you're trying to grow, it can be very valuable. If you're growing a lot of lettuce, a lot of leafy greens, things of that nature, it might be more beneficial to discard some of that out of your system because of the phosphorus and other nutrients that are going to be breaking down that might not be the correct nutrient solution for growing these leafy green crops. But we'll get all into that extremely extensively as we go forward. So some system improvements. There are several things we can do to improve the efficiency of the culture tank design. The addition of vertical outlet manifold in those 2,000-gallon tanks would really help to move the waste out of the tanks quicker, giving you better water quality, lower ammonia, faster removal of solids out of the system, and actually higher oxygen levels because we don't have those organics degrading in the water column. So all positives from a simple addition of maybe a $30 piece of plumbing. We want to add a manometer to that. So that's our clear pipe. I think we'll talk about that in a little bit. It's basically a sight pipe that gives us an indication of flow. Well, something that the University of Virgin Islands does is they adjust their water flow in the culture tanks depending on the size of the cohort in those culture tanks. So what does that mean? That means the tank with the most fish that are closest to harvest gets the most water flow. And the tank that doesn't have many fish, that is full of fingerlings, is going to get relatively less water flow. Well, without actually having a flow meter or having a manometer, you're just guessing as to how much water you're putting into each one of those tanks, unless you take a physical measurement with a 5-gallon bucket or something like that. So a quick little addition of a clear manometer sight tube would actually allow them to adjust those levels perfectly to say, we want 70% of the water going here, 20% here, 10 and 5, or whatever they decide. But they could do it all by this clear sight tube, which we'll get into the construction of here shortly. Calculated pipe size for self-cleaning and efficiency. So we already kind of discussed that. It would be easier and it would be cheaper for the build. More efficient mechanical filtration. So they build a cone bottom clarifier with a baffle. It's basically a large cylindrical cone bottom tank with a 45-degree bottom with a hole. So the waste captures there. When we open a valve, it sucks the wastes out of the bottom of that cone and takes them to their stabilization pond. Well, in the middle of the filter is a large wall. So the water actually has to go down under the wall, travel back up, and then out of the tank. On that downward journey where the direction changes, that's where the solids drop out and get captured in the bottom of the cone. They also stock some tilapia in this tank to help keep solids moving down that cone closer to the drain, but sometimes they stir up those solids. Well, we'll talk a little bit about this later, but we can actually shrink that filter probably by 3 to 4 times, which would be a lot less expensive and a lot easier to maintain. We'll actually pull out more solids with a filter that's 1/3 to 1/4 the size of these filters. So that's somewhere we can improve this design. So let's talk about vertical water outlet manifolds. How do we design these? We've talked about them in the aquaculture section. I think we've seen some pictures, but this is basically the water pipe that's putting water into your fish culture tank. So they should be constructed for proper water flow distribution. So instead of water just having a single injection point, say at the top of your tank, which is very common to see in aquaculture facilities or just backyarders that are putting together a fish system, we actually want to take that pipe and bring it all the way down to the bottom of the fish tank. And we're going to drill equal holes so that instead of just rotating the top portion of the tank, we're rotating the entire water volume inside of that fish culture tank. And by creating that rotational velocity, it's just what we've been talking about this entire time. That's what allows these tanks to become self-cleaning. So a single vertical manifold, I would suggest for tanks 1,200 gallons or 4,600 liters and under. You can get by with a single one, no problem. Dual vertical manifolds are for tanks between 1,200 gallons and 10,000 gallons. So when we start getting bigger, we want to use one on each side of the tank to keep that flow and the rotation going steady and evenly. Or you can do these for smaller systems when you don't want to use a large pipe in the tank. So say you're doing a backyard system and after you do the calculations, it tells you it should be a 2-inch pipe going down to the bottom of the tank. But maybe you only have 1-inch pipe. Well, do the calculations for 1-inch pipe, and after you do them, I'm sure you can figure it out. It will tell you that you can have one manifold on each side of the tank. You drill the holes, you get the flow rates that we're going to go through here. But basically, I would just say small tank. If you really want to use small pipes, you can do that. I think it's easier just to use a single manifold. The use of a horizontal manifold in addition to the vertical manifold have been proven beneficial on tanks with diameters greater than 15 feet. So instead of our single down pipe, we actually have a crossbar that goes out and actually is moving the surface of the water as well, helping to move the inner portion of that fish culture tank to help that water start to rotate and keep an even rotation throughout the water column. So the best placement is 1/4 the radius of the fish culture tank from the sidewall. So that leaves room for fish to swim between the manifold and the sidewall. So if you measure down to the center of your tank, straight up, and then you go to the sidewall of your tank, 1/4 of that distance from the center to the sidewall is how far off of the sidewall this vertical down pipe should be placed. the best angle for self-cleaning is if you point the injection stream at 1/6 the circumference of the culture tank. So if you take the entire circumference of the culture tank and you divide it by 6, that distance is where you want to aim the jet stream to create the fastest rotation within the tank. Now, if you rotate it closer to the wall, you're going to slow the rotation while keeping the same water turnover in that tank. So you're still going to process ammonia just as fast. It's going to go through the biofilter just as fast, but you're going to slow the rotational velocity, which is great because for younger fish, we need a little slower rotation. And as they get older, we can just turn that vertical manifold out, increasing the rotational velocity in the tank and providing the correct environment. So the pipe velocity in this downpipe should not exceed 2 to 2.6 feet per second. That's 60 to 80 centimeters per second. Or most of the water is going to exit through the lower holes. So what that means is when we drill, say, 8 holes all the way down this manifold, if we have too much pressure, it's going to force most of the water out of the bottom holes. It's too much pressure. So this is the correct pressure, the correct velocity, and you'll get even flow out of the holes going down that vertical manifold. The outlet hole size is calculated based on the total water flow and the length of the vertical manifold to create minimal friction losses. So in this example, we are going to design a vertical manifold for 20 gallons per minute in a 4 feet deep culture tank. So 4 foot deep of water volume, and we know our water volume that we're pumping is 20 gallons per minute. We want to place holes evenly every 6 inches, starting at 4 inches below the surface of the water, and then ending at 2 inches from the bottom of the tank. Now, I usually like to glue the cap on the bottom of the vertical manifold and then drill a hole right above that seam. That's usually the first hole. But if you get into bigger pipe like 4 or 6 inch pipe and the cap's big, you actually will drill through the cap for your first hole. So it gets a little closer to the bottom of the tank. We're going to place holes evenly every 6 inches, starting, we just said that, I'm sorry. And then, so here's the math, 48 inches minus 6 inches, because that's the 4 inches off the top and the 2 off the bottom, gives us 42 inches of pipe within we want to actually drill our holes. Well, 42 divided by 6 inches, a hole every 6 inches, gives us 7 holes total. So we know through this 42 inches, we're going to have 7 holes evenly spaced every 6 inches. But what size are those holes? Well, 20 gallons per minute divided by 7 holes is 2.86 gallons per minute per hole. So that's just to let you know how much we're flowing through each hole. I don't think that's really something you need to know for the next formula though. That's just to give you an idea. So in order to size the holes, we must solve for V equals Q over A. We will come back to this on slide 23 after we have actually talked about V equals Q over A, and we know how to do that equation. Very simple, but that will tell us the answer to how we figure out that hole size. So we'll come back to this on slide 23. Manometer design. Now the manometer gives us a visual indication of the flow rate and works based on the differential back pressure within the vertical manifold. So we actually have to create a little bit of back pressure. And by creating that back pressure, it allows water to flow up into this manometer and give us a visual representation. So, you know, we talked about flow rate needs to be close to 2 feet per second for this manifold. Well, or the velocity coming out of those holes. Well, if the velocity was 0, or let's say the velocity was, 0.2, it was real low, we had huge holes drilled in that pipe, there would be no back pressure, so we wouldn't get any water flowing up into this manometer. And once I show you a picture here on the next slide, it'll make a little more sense. This manometer can be added by installation of a reducing T, 60% of the main shaft size, a 90-degree elbow pointed up, and a clear sight tube. So clear PVC or acrylic if you get a PVC to acrylic fitting, because acrylic doesn't fit into PVC fittings. But you do this at water level pointed up. The length of the clear sight tube depends on how much differential back pressure you actually design into this. So this is a picture of one. Unfortunately, it's a little dirty. This has been in use for 2 years in a tank, But you can see here's our down pipe all the way to the bottom. We've got a union that we put right above our T. So we've got a T, a union, and then our elbow that goes over the side of the tank right to the main water line that's feeding this water. As the water comes in, it goes down, there's a cap, and it has to come out of these evenly spaced holes. And that rotates the water very well and makes this a self-cleaning culture tank. Here you see a reducing T. It comes straight up, and that's clear PVC. Now you can see how it's a little green. That's because this fills with nutrient-rich water. It fills with the culture tank water, and because some sun actually gets into my fish culture room, you get algae that grows in that sight tube. So I'm getting ready to do a cleaning job. We go ahead and put a little scrub brush in there, do that once a month, and it ends up staying clean, not a problem. But very simple. You can see this is PVC pipe, a T, an elbow, clear PVC, a union, and a cap. And you might buy that for a couple $100. If you go out and buy a calibrated manometer, something like that, you can build that for, the union's the most expensive part, but $20 to $30, something like that. So these are the areas that you save money and still keep your system professional, still use the technology that's out there right now that we want to use. So here's two more. You know, right after you built them and glued them together, I know these are actually a little old. I've got several for a new project that we're getting ready to start. But you can see very clearly, holes drilled. Right here, I just don't have an elbow in with a clear sight tube up yet. But those are manufactured. You can, you know, you need to knock 10 of them out. You can do it in a couple hours. It's not that hard to do. So here we're going to learn V equals Q over A, like we just talked about a minute ago. So velocity through a gravity or unpressurized line. So that means if we're flowing by gravity, not pushing with a pump, but if water is naturally flowing from point A to a lower point B, using gravity, the optimal velocity is 2 feet per second. This means solids won't settle in the pipe, and we still have low friction and low head loss going through that pipe. So we don't have to have huge drops between the components to actually make water move. For a pressurized line, so on the business end of a pump where the water is picked up, pushed through the pump, and it's being forced to the culture tanks, you want the velocity at 5 feet per second. This does not require excessive head pressure, and excessive head pressure means higher energy input. So if the piping's too small, if there's too much friction, the pump has to work harder to do the same job. So this is a good reference point to size a water pump on any kind of pressurized line. And 5 feet per second is optimum, though I've seen professionals in the industry size all the way up to 7 feet per second, depending on the pump, the pump's flow curve, and where the best efficiency is for the pump to run within that flow curve. And we're going to talk all about that when we get to picking out equipment and we go through water pumps and talk about that. So V equals Q over A. V is velocity in feet per second or meters per minute. Q is flow rate in gallons per minute or liters per minute. And A is the cross-sectional area. So this area here, that distance, area in blue. So remember that the area for a circle is pi r squared, or pi times the diameter squared divided by 4. So this is geometry. I didn't make these equations up, but we need to use these. We need to reach back to that school geometry class and use these again. And they're really going to help us create an efficient system. So for my examples, I prefer to use pi times d squared divided by 4. That's why I'm going to be using in the next example. By all means, use pi r squared if you want to use that formula. We get to the same place. So calculate the velocity for 100 gallons per minute going through 3-inch PVC pipe. Well, if you look at a chart, 3-inch PVC pipe, the internal diameter is actually 3.068 inches. And when we're engineering, we want to use actual numbers. We don't want to just round to 3 inches right off the bat. Round on your last number of the equation, not through every number in the equation, or you might be off a little bit on your last answer. So Q, and just bear with me if you don't like math, this is very easy and you're going to just be able to plug your numbers in and get the answer. So Q equals 100 gallons per minute. We know that. It's given up there, okay? 1 cubic foot of water equals 7.48 gallons. So that's just a conversion that's added into this formula to get us the right answer. That's a given. 1 minute equals 60 seconds. That's a given. Okay, so everything's given here. All we needed to do is plug in 100. This is very easy. 100 divided by 7.48 equals 13.37. 13.37 divided by 60 gives us 0.22 cubic feet per second. We just solved for Q. Okay, we've got half of this done. It was very easy. One multiplication, or here we go. I'm sorry, one division, second division, answer. Really easy stuff. A, so we're going to say pi times 3.068 inches times 1 over 12 squared divided by 4. Remember I told you that formula we're going to use on the last page. This is it with the numbers plugged in. 3.068 divided by 12 equals 0.256. 0.256 squared equals 0.066. 0.066 times pi, which is 3.14159, equals 0.207. And then finally, we're going to divide it by 4, and it gives us 0.052. Now, I know that's a lot of numbers, but that is simple math. And you guys can do that if you just plug your number into this slide, write it out on a piece of paper, plug your number in, do the same math. You can make this work. So what do? We got to divide those two numbers. Now we put it back in our main equation. We solved for Q, then we solved for A. When we do the division, we get 4.23 feet per second. And that's the answer we want. We want to know how many feet per second is the velocity going through these pipes. 4.23, that sounds just fine for a pressurized line. It's not quite 5, but it's getting close to it, and it's still fast enough that it's going to keep any kind of solids from settling in the pipe. And what you could do is you could use a different size pipe. Say you weren't happy with 4.23 inches on a 3-inch pipe. Well, do the number for a 2-inch pipe and see what happens. So we're going to do that right now. Calculate the same velocity through a 2-inch pipe. And we've got a lot of math through this session, so this is the exact same math we just did. We just used 2 inches instead of 3 inches. So we'll kind of go through this, but the numbers we get, Q equals 0.22 and A equals 0.024. When we do the division, we get 9.16 feet per second. I think there's a clear winner between 2-inch pipe and 3-inch pipe. So sometimes you have to do more than one calculation to assure yourself you're making the right decision, because it's almost never going to be the exact number that we want to shoot for. It'll almost never be exactly 5 feet per second, but you want to get as close to that standard as possible. Now that we know how to solve for velocity, we can size the holes for that vertical manifold that we talked about, and we said we'd be back on slide 23. Well, here we are, and we know how to do V equals Q over A. So we're going to do 20 gallons per minute using 2-inch pipe. Q ends up equaling 0.045 cubic feet per second. A equals 0.024, and then we divide these two. 0.045 Q divided by 0.024 A, and it gives us 1.875 feet per second. And again, we want it to be below 2 to 2.6 feet per second. Above that creates too much pressure, and we're going to get unequal distribution through those outlet holes. But a little bit under 2 feet per second, that's not going to hurt us at all. We're not going to get any settling in a vertical pipe, so that's not a problem. So this is the correct size, 2 inches, okay? But we need little holes, 2-inch. We don't want one large 2-inch hole. We want little holes. So what do? We know we have 1.875 feet per second, 2-inch down pipe. Well, we divide that 2-inch pipe by the 7 holes we calculated earlier. We already know we wanted to make 7 holes for an equal distribution down that distance of the manifold. So 2 inches divided by 7 equals 0.29 inch holes. So a 9/32 inch drill bit equals 0.28 inch. A 19/64 inch drill bit equals 0.297 inch. So personally, I would choose the 0.28 because if we know at 0.29 we're getting 1.875 feet per second, making that hole just 1/100th smaller is actually going to increase this just slightly, and that'll be closer to our 2 feet per second. So we would choose that drill bit, drill our 7 holes, and you have the manifold that you wanted to make. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.